Hello everyone, my name is Shutian. Today I'm going to give a presentation on our paper, Erms, Efficient Resource Management for Shared Microservice with SLA Guarantees. The work collaborates with SIAT, the University of Macau, and Alibaba Group. Here is the outline of the presentation. I will introduce the background first. Microservices are developed for monolithic applications. A monolithic application could be divided into a set of lightweight and loosely coupled microservices. Monolithic application usually runs in a single instance, like virtual machines, and contains multiple modules. Each module can be developed to an individual microservice. Microservice usually runs in containers and communicates with each other by network. Take an online shopping service in Alibaba as example. The calls between microservices are very complicated in the production cluster. Moreover, microservice architecture is very popular in the internet companies. Its scales and complexities are increasing gradually. Benefit from microservice fine granularity. There are some advantages of microservice architectures, like ease of management, maintenance, and update. Here, I will introduce the microservice dependency graph. Look at the figure. A request from users will trigger a series of calls between related microservices, and such set of microservices with dependencies forms a graph. Each node in the graph represents a microservice. Each edge is a call between a pair of microservices. Moreover, the end-to-end latency of an online service is the duration from user sending a request to it receiving the reply. It is important to improve resource efficiency for microservices. The reason is that microservices are over-provisioning to ensure performance. Alibaba trace analysis indicates that microservice latencies are stable when the call rate varies, as shown in the figure, and the average of microservice resource utilization is less than 10% in the production cluster. There are three main challenges for microservice resource management. First, it is difficult to scale resource at the granularity of microservice while satisfying SLA requirements. The reason is that there is parallel and sequential calls between microservices in a dependency graph. Moreover, the end-to-end latency is related to each microservice in the graph. Therefore, scaling each microservice while meeting the end-to-end latency of dependency graph is challenging for an online service. Second, microservices are shared by different online services. The figure shows that 40% of microservices are shared by more than 100 online services. Services have diverse workload patterns and different SLA requirements. It is challenging to satisfy SLA requirements for different online services at the same time. Existing words does not consider the microservice multiplexing. Third, resource interference is non-uniform. For example, the trace analysis on Alibaba cluster indicates that the resource utilization varies among the physical machines as shown in the figure. It will cause the performance imbalancing between containers from the same microservice, as a microservice usually has hundreds to thousands of containers in the production cluster. We have some good observations to address the challenges just mentioned. First, we observe that the latency of most microservices can be formulated with a piecewise linear function as shown in the figure. In the figure, the two numbers in each bracket are the host CPU and memory utilization, which represent resource interference. Slope and the cutoff point of the latency model depends on the workload and resource interference. We can balance the resource utilization in the cluster to ensure microservice latency. More importantly, we can use the piecewise linear models to optimize the resource configurations globally for all microservices. Such a simple models can be leveraged to handle larger dependency graphs efficiently. Here, I will further introduce how to use the latency model to decide the latency target for each microservice in dependency graph for resource allocation. The slope of microservice latency models can be regarded as the performance sensitive intuitively. Take a simple sequential course that Microservice use called Microservice P as an example. The latency model of Microservice U has a higher slope. That is, Microservice U is more latency sensitive. Allocating a fewer resource on Microservice U can save allocated resource on Microservice P greatly and reduce the end-to-end latency significantly. Therefore, our systems will allocate higher latency target to latency-sensitive microservice. We find that implementing priority scheduling on shared microservice can improve resource efficiency. Take two microservice trains as an example in which Microservice P is shared by Microservice U and H. The latency target on Microservice P in two trains is different. Sharing is better to reduce means processing time. However, we need to satisfy the tail latency for SLA requirement. Intuitively, the trains with lower latency targets on Microservice P will be straggled by another one. So it needs to allocate more resource to Microservice P to satisfy the low latency target in the sharing situation compared to non-sharing. In this case, non-sharing can reduce the allocated resource, but non-sharing will violate the principle of microservice loss coupling. Instead, we implement priorities on shared Microservice P for the trains with lower latency target. Notice that we need to recompute latency targets of microservice due to the trends of workload order. Such priority scheduling can keep the principle of loss coupling. Importantly, it can save the resource via the global coordinations on two trains. For example, increasing a few resources for Microservice H can reduce much resource on Microservice P. Based on the observations, we build an basis models to allocate resources for microservice with SLA guarantees. To do so, we compute the optimal latency targets for each microservice with a given dependency graph, latency models, workload, and SLA requirement. Specifically, we formulate an optimization problem and achieve the close-one results for optimal latency target. In the coming slides, I will introduce our design Erms and give more details about how Erms handle a complicated dependency graph. I mainly introduce three modules of Erms, including offline profiling, online scaling, and online scheduling. Offline profiling modules adopt a piecewise linear functions to fit the microservice latency and learns the parameters of the function from the historical trace. The slope is decided by resource interference in the function. Importantly, the model can contain multiple resource interference easily. Next, the online scaling module is to compute the optimal latency target for complicated microservice dependency graph. First, Erms will merge the dependencies to simplify the complicated dependency graph through the depth-first search as shown in the figure. In particular, Erms will merge microservice with sequential or parallel calls as virtual microservice based on the latency model. Second, we will reverse the ASPLOS graph merge procedures to compute a latency target for each microservice. Specifically, we compute the latency target for virtual microservice based on the SLA and divide the virtual microservice into original microservice. After that, we implement the priority-based scheduling on the shared microservice. However, it is expensive to achieve the optimal solutions for large numbers of shared microservice. So we adopt a heuristic solution to allocate higher priorities on the online service with lower microservice latency target. Such a solution can reduce overhead greatly. Workload orders on shared microservice has changed with the priority-based scheduling, so we update the latency targets for all microservices to optimize resource allocations for multiple online services globally. For the online scheduling module, we formulate an optimization problem to balance resource utilizations in the cluster to mitigate the performance imbalancing of the containers from the same microservice. Such a problem turns out to be NP-hard. So we simplified it as a linear optimization problem and divided the cluster into different groups to mitigate the scale of the problem. We evaluate the systems on local cluster using Delta Bench and Alibaba Trace. Erms has passed the artifact evaluations and received 3 badges. I will give the main results in the following slides. The evaluation using benchmarks shows that Erms can save about 60% of allocated containers and reduce the SLA violation probability by 5 times on average compared to the baseline schemes. We replaced the trace from Alibaba production cluster to evaluate Erms and the baseline schemes. The result shows that Erms can reduce the number of allocated containers by 1.6 times on average compared to the baseline schemes. Moreover, Erms can be used in the production cluster with lower overhead. In summary, we are the first to mention resource for shared microservice. 2 key techniques is to compute the latency target for microservice with complicated dependency graph and implement the priority-based scheduling for shared microservice. The system has limitation is that it tends to allocate over-provisioning resource for microservice with highly dynamic dependency graph. Our future work is going to address this problem. Thanks for your listening.